No. Okay. So mathematical induction is a way of, formally proving mathematical conjectures, right? So it's called the principle of mathematical induction. The process involves 3 steps, and they can be they're as follows. So first of all, when you have a conjecture, right, show that it works for the first case, like when n equals 1. We call that the anchor step. Okay? All right, so let's see. If n equals 1 is what you're saying going to make sense. Okay, yes, it's true. Now, assume, so these are like having to do with, the whole world of numbers, right? So assume that it works for any particular case n equals k. So just pick a random k, like pick a random number, and let's assume that it works for that one. Now, if you can show that it works for the case immediately following for n equals k plus 1, then you've proven the conjecture. All right? So you prove it for any random number, and you're like, okay, maybe we got lucky. Now, if it works for the very next number, then you're good. Okay? All right, so let's do this first one. Use mathematical induction to prove that the sum of the first n odd positive integers is n squared. So the first n odd positive integers, so 1, 3, 5, and so on, is equal to n squared. So if you take the first however many, like if you take the first 10, the sum would be 10 squared. If you take the first 5, the sum would be 5 squared. That's what it's saying, okay? That is, so to put it in more mathematical terms, prove that 1 plus 3 plus 5, until the last one is 2n minus 1 is equal to n squared, right? So basically, the first term is 1, the second term is 3, the third term is 5. What would the fifth term be?
7.
The fifth term.
9. Oh, okay.
9. So if it's the fifth term, it's 9, or it's 5 times 2 minus 1.
Yeah.
You get it?
Yeah.
Okay? Okay? All right, so...
Wait, it doesn't work for...
Yeah, okay, so... Huh?
Because 1 times 2 minus 1 is 3.
Okay, here we go. This is n equals 1, 2, 3, 4. The first number is 1. The second number is 3, then 5, then 7, then 9, then 11. Are we okay with this?
How do you know there's only 6?
Okay, oh my gosh. Okay, hang on. There isn't only 6. I just chose 6 right now. Okay? Now, take a look. If I want the fifth number, what is it? 9. How else? I could either count up 1, 3, 5, 7, 9, or if it's the fifth number, 5 times 2 minus 1, that's 9, isn't it? Okay, the sixth number, 6 times 2 minus 1, 11. So the 34th number, how much?
34 times 2
Right.
minus 1.
Okay. So this just tells you that you have a list of odd numbers until whatever, that number. This list can represent 6 numbers, or 600 numbers, or 5,000 numbers. We don't know, we don't care. The point is, however many numbers are on this list, if I add them all up, I'm going to get n squared. So if I have 6 numbers, 1, 3, 5, 7, 9, 11, if I add them, I'm going to get 36. Is that true?
Yeah.
Yeah, if you add them, you get 36. Okay, but now we're going to prove it for all the numbers in the world. Okay, once and for all. So let's just do that. Okay. Okay, so let's explore a little bit more here. Okay, let's just explore a little bit. Suppose n equals 6, just like I had before. 1, 3, 5, 7, 9, 11. Is that 6? So we said that that's going to equal 6 squared, right? Okay. Suppose now I add one more to that list. What happens? 11 plus 13. Now it's not going to be 6 squared anymore. It's going to be 7 squared anymore. So suppose I had n of them. This was n squared, right? Now, so n is 6. So if that's n, I have n squared. How is this related to n? N plus 1. So the last one is n plus 1 squared. Do you see what happens if you add 1? Okay, so we're just getting used to some numbers here. All right, let's start our proof now. The first one is show that it works for the first case. So if n equals 1, I only have, what do I have in my list? 1. And that equals 1 squared. Is that true? Yeah, it's true. Okay, assume that it works for n equals k. So you say to your buddy who's trying to like pull this one on you, you say, okay, I'll just assume that it works for n equals k, which means blah, 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 plus 2k minus 1 is equal to k squared. Is that true? It's true. Yeah, you just assume. Okay? Now, because the thing is, if you assume that it works for some random number and you show that it works for the one right after, right? Because what are the chances that you win the lottery and then you win the lottery again the next day, right? I mean, that means like you're just going to win the lottery forever, okay? Okay, it's not quite like that, but you get the idea. I'm exaggerating a little bit. So now, let's see, once you assume that it works for n equals k, if you can prove it for n equals k plus 1, then you're done. So that means just like here above when I had 6 and 7, when I went 1 up, I added an additional term, right? So that's what I'm going to do here. I'm going to add an additional term. So check out what I'm going to do. First, I'm just going to copy over everything that I have. Leave a little bit of a space here. Okay, I just copied down what I have. I'm going to leave a little bit more space. Do you see what I did? Just copied it down. Okay, so here I'm going to add another term. So now, when I had k terms, the last term was 2k minus 1. When I have k plus 1 terms, the last one is 2 times this minus 1. Okay, so it's going to be 2k plus 1 minus 1. I never leave enough room there. Okay? Yeah. Now, I changed my equation. I can't do that. I need to keep it balanced. So I'm just going to add the same thing here. All right. So now take a look at what we're going to do. I'm just going to copy this over. 1 plus 3 plus 5 plus plus 2k minus 1 plus, just leave it like this, is equal to, what do I have here? Let's distribute k squared plus 2k plus 2 minus 1. Okay, can I just write that as k plus 1? Okay. So 1 plus 3 plus 5 plus plus 2k minus 1 plus 2. So the one with one more term, let's see what it equals. What do you get when you factor this? K plus 1 squared. What should I have gotten? N plus 1 squared. K plus 1 squared. So you proved it. You see that? You proved it. What you showed is assume that for k, it's k squared. And then if I add one more term here, is this going to equal k plus 1 squared? Yeah, it is. So this is done. You just proved it. Yes?
Are we ever going to get in a case where it's not true?
No, because it says, it literally says prove that, which means it's true and you're proving it. Yeah. Well, yes and no, because then if you can't prove it, then...
Yeah, then you know you're wrong.
Yeah. Okay. So what I like to do is kind of work backwards a little bit. I didn't do this by accident. I like to do that so I know what I'm supposed to be working towards. Okay, so let's do it again. Now the first n, okay, so prove that the sum of the first n even positive integers is n squared plus n, meaning 2 plus 4 plus 6 is plus 2n is n squared plus n. Yeah. Yeah, that'd be nice. Okay, so let's explore a little. Okay, if let's say n equals 4, I get 2 plus 4 plus 6 plus 8 equal to n squared plus n. 4 squared plus 4. Well, 2n is just the last term. And how do you get the last term? You can either count up to it or do it that way. So now when I increase it to 5, I'm going to get 2, 4, 6, 8, 10 equal to 5 squared plus 5, right? So now, if my first number was n, I had n squared plus n, or k squared plus k. But now I went up 1, and what happened here? That's no longer k. How does that relate to k? K plus 1 squared plus k plus 1, sorry. So let's see, so this is what we want, okay? We should get this. Okay, we should get this. Okay, so let's see if we're going to get that. Okay, so let's see it for n equals 1. Does it work? If n equals 1, what's in my list? 2. And does that equal 1 squared plus 1? Yep. Okay. If n equals k, I just copy that here. Right? Now, n equals k plus 1 means I have the same thing, and then here equals k squared plus k, but now I'm going to insert one additional term, right? So let's see. The last term in this list is always 2n. If n equals k, then it's 2k. If n equals 2k plus 1, then it's 2k plus 1. So here I add the same thing. Okay? All right, now take a look at what's going to happen here. I'm going to just work on the right side. So k squared plus k plus 2k plus 2. Remember, what I want to do is I want to make this look like that. Okay? And with that, with these, you're free to do anything you want as long as it's mathematically viable. Okay? So, take a look at what we're going to do. Don't miss this now. Just for fun, you see how there's a plus 2 here? Okay, so if I ask you how old you are, you could either say you're 17 or you could say 3 plus 14, right? And if that's a 2, it's either a 2 or a 1 plus 1. Let's just write that as 1 plus 1. In fact, I'm going to do something else. I'm going to do this. I'm going to group these together. The k squared, the 2k, and the 1 together. Yeah, because why not? What's left? Hang on. Look. What's left over? K plus 1. Okay, here's how you know. Here's why we do it. What's the black factored? Oh my goodness. Plus what? What should we have gotten? That. So now you ask yourself, and this is what I would ask myself all the time when I was in these classes. Okay, how do you know to do this? Because my teacher, and then it was my professor, and you know, they would all just go, oh, then of course we can write this as 1 plus 1, and how do you know to do it? And the only answer I could give you is, when you see enough of them, you just know. Okay, that's really what it is. Okay, so 2 plus 4 plus 6 plus ... plus 2k plus 2k plus 1 is equal to that. Yeah.